lecture we were talking about something called SU2 group. Now the word SU2, it simply means special unitary. So it is basically a unitary group which has got certain special properties. Now, before going into SU2, we need to first understand what actually this unitary group means. Now, n into n vector space, you can represent a unitary group by un. Now, a unitary group is a combination of all those unitary transformations which are present in this n into n vector space. Now, what do we actually mean by unitary transformation? For that, we need to understand what a unitary matrix is. A unitary matrix is that matrix whose complex conjugate transpose, that is U star and dash. It means first you do the complex conjugation and then you do the transpose, and this is represented by U dagger. If this is equal to the inverse of the matrix, then we can call it a unitary matrix, or it can be represented as U dagger U equal to U dagger equal to I. I stands for a identity matrix. Let us take an example. Suppose we have a matrix U as, say, A, B, C, D. So U dagger will be A bar, D bar, B bar and C bar. So this is the complex conjugate transpose. Okay. Now, what is a unitary transformation? Unitary transformation is that transformation which keeps the inner product, which actually preserves the inner product. Now, what do we actually mean by inner product? So this word has to be understood. Inner product preservation. Now, as we have defined a unitary matrix, you again write U dagger is equal to I. That means A, B, C, D into A bar, B bar, C bar into D bar equal to 1, 0, 0, 1. Now if we do the matrix multiplication, that means if we multiply this one with this one, and again this one with this one, and again we multiply this matrix, again this matrix with this matrix, so we will have the following 4 equations. First, let us write those matrices one again. A, B, C, D, A bar, B bar, C bar and D bar. This stands for the conjugate, is equal to 1, 0, 0, 1. So A bar plus B bar is equal to 1. Then A C bar plus B D bar is equal to 0. Then C A bar plus D B bar is equal to again 0, and C bar plus D bar is equal to 1. So what does these equations mean? It means that AB, the vector AB and the vector represented by CD, they are orthogonal to each other, and they are also, so this orthogonality is represented by these 2 equations, this equation and this equation, whereas they are also unit vectors, okay, because their modulus value is 1, so they are also unit vectors. Now this multiplication or this matrix, this with this is actually the inner product. This is what we actually mean by inner product, and usually we can represent this as U0 and U1. So it means that it actually means that if a rotation is taking place in a vector space, then the inner product is being preserved. This is actually what is meant by a unitary transformation. So this is the preservation of the inner product is done in unitary transformation. So this is what we initially started with. Initially started with unitary transformation, and so all the unitary transformations in an end-to-end vector space, they form the unitary group, and one of the unitary group is your SU2 group. Now what are the interesting thing about this SU2 group is that so let me write it this way. The interesting thing about SU2 group is an SU2 group is a 2 cross 2 group, and it has a determinant value Now this group is again a reducible group. Now there are two types of group. One is reducible and one is irreducible. Now how do we define a reducible and irreducible? First of all, any rotation or any transformation that is represented by a matrix can define a lot of transformations. It can define it can represent a rotation, it can represent a translation, it can define mirror images. So all these are represented by a matrix. Now if a matrix can be simplified into matrices of smaller dimensions or smaller order, then we can call it a reducible transformation. If it is not, then it is a reducible transformation. So an SU2 is a reducible transformation, and it can break up into, so initially it was a 2 cross 2 matrix, so it can actually break up into 3 plus 1 reduction, and 3 plus 1 means there is a 3-dimensional representation, a 3D representation, and there is a 1-dimensional representation. Now coming to elementary particles, if you look at my previous lectures on elementary particles, the pion group means pi, plus, minus and pi 0. These three elementary particles, they will correspond to this 3-dimensional representation. We have almost equal mass. Almost equal mass, and they are also identical in terms of strong interaction. So identical strong interaction. Okay. Now similar to SU2, we can have another transformation which is called an SU3 transformation. An SU3 transformation. So from the name itself you can understand it's a special unitary transformation in a 3 cross 3 matrix, 3 cross 3 vector space. Now this 3 cross 3 can be further, it is also a reducible transformation. It can be broken down into 8 plus 1 representations. Now this 8 is again means it is the 8 baryons. And neutron, proton, sigma plus minus sigma 0, psi minus and psi 0 and lambda. These 8 baryons are represented by these 8 transformations. And also the 8 mesons, that means pi plus minus pi 0, k plus minus k 0, k bar 0 and eta 0. These 8 transformations are again represented by this 8, and we can similar consider actually this 8 is not represented by this but by another breaking of this SU2, that is we have 3 cross 3 cross 3. It can be broken down into 10 plus 8 plus 8 plus 1. So the 10 baryons, this represents the 10 baryons, and this represents the 8 mesons. This is the famous 8-fold way of, as suggested by Gell-Mann. And you actually basically get an octet. If you have y versus I, you basically get an octet for this.